Hello, everyone. Welcome back to the TAUP conference. In this session, we're going to be talking about and discussing axions. Our first speaker, Javier, is going to tell us about axions as dark matter, and he's going to review both the theory and the experiments. Let me remind you that if you have questions, please enter them into the Q&A, or feel free to use the discussion boards that the conference organizers have provided. Take it away, Javier.
Lovely. Can you hear me and see my slides?
Yes, I can hear you and see your slides.
Fantastic. So let us begin. So thank you very much, organizers, for inviting me to give this talk. My name is Javier Redondo, and I'm based at the University of Zaragoza and Max Planck Institute in Munich. And it is my duty to review the status of axions as dark matter, both from a theory and experimental side. So I will try to do something very basic so that all people can not acquainted with axions can get acquainted, and you can get some new information, some fresh information piece. So the outline of my talk is just I shall be briefly touching on the strong CP problem and the axion solution, and further motivations to consider the axion's existence, and then also talk about later axion dark matter and how to find axion dark matter in experiments. Very well. So our tour begins with the observation that actually CP violation or CP symmetry, discrete symmetry, is violated in nature, and in particular in the electroweak interactions, as it has been established already in the 90s by the CP collaboration at CERN by measuring the asymmetry of the decay, or this asymmetry, which measures the asymmetry of the decay of neutral kaons and the CP conjugates, as you can see here. However, this is not the case in the strong interactions. In the strong interactions, CP violation has never been observed. And this is quite strange, because quantum chromodynamics, which is our best theory, or our theory to describe the strong interactions, although it has a P and parity and time reversal conserving piece, and perhaps it's the most important, it has also a CP violating term built in this structure, and we tend to forget this. And although we tend to forget this term, we should not, because it is the sum of two contributions. One defines the QCD vacuum, and is a piece of which is intrinsically defined in QCD, and the other is the argument of the determinant of the quark mass matrix, which is has the same origin as electroweak CP violation, which is quark mass phases, and we have observed already CP violation in the electroweak sector. So we expect generically that this term in the Lagrangian, which is formed with the gluonic fields and is proportional to the theta angle, the theta parameter, which is an angle, will induce parity and time reversal violation, which is proportional to the value of theta. And well, the most celebrated implication of this term is that neutrons and other hadrons will get an electric dipole moment, which is going to be proportional to the value of theta. And this can be in principle measured. However, this can be measured, for instance, like studying the spin precession of neutrons in configurations that have an electric field pointing in two directions that should imply a difference of the precession frequency given by these expressions. However, these searches have consistently reported only upper limits on the electric dipole moment of the neutron, and so this has been not observed, and this actually renders upper limits on theta, which are amazingly small, of the order of 10 to the minus 10. So this makes theta one of the smallest parameters of the standard model, or perhaps the smallest parameter of the standard model, if you say that neutrino masses are beyond the standard model. And well, it is actually the smallness of this value and the fact that it is the sum of two a priori unrelated quantities that makes the so-called strong CP problem, right? So why is theta so small? And well, in the 80s, late 80s, Roberto Peccei and Helen Quinn proposed an explanation of a possible explanation for the smallness of theta. In essence, what they realized is that the value of theta controls the vacuum energy of QCD, and the vacuum, and then the value of theta that minimizes the energy of QCD, so the vacuum energy of QCD is precisely theta equals 0, and therefore also minimizes CP violation. Therefore, what Peche-Quinn pointed out is that if theta would be a dynamical field, then its vacuum expectation value would evolve automatically with time and automatically end up in the CP conserving value. Now, immediately, Weinberg and Wilczek realized that the mechanism used by Peche and Quinn, which was a global, or to introduce a global U1 axial symmetry, which was spontaneously broken at some scale, would imply the existence of a new particle, the Goldstone boson of the new symmetry that Peche-Quinn has predicted. Now, this particle was called the Axion because it was reminding Frank Wilczek its favorite detergent, and it was appearing here from an axial symmetry to clean up the mess of the strong CP problem. And this axion corresponds to nothing but the oscillations of the axion field around the minimum. Now, perhaps the most important implication of all this is that since the lifetime of the universe is finite, the axion field, whatever its initial conditions were in the beginning of the universe, it wouldn't have had time to completely relax to 0. And therefore, one predicts or expects that the axion field is still oscillating around the minimum of its potential with a very small amplitude. However, this small oscillation around the minimum stores energy, and very soon after the proposition of the axion, these three groups realized that actually these oscillations, the energy in these oscillations behaves exactly as very cold dark matter. So the same mechanism that solves the strong CP problem by rendering theta to 0 essentially predicts the existence of some form of cold dark matter. Now, as a side remark, it is fun to note that at least in one sense, the axion field is not relaxing. So the axion research field is actually not relaxed in any way, but is actually becoming increasingly excited, as you can see here from the large number of papers with keyword axion that appear in Inspire every year, that is approaching dangerously 1,000 a year or so, as the interest of the community for these particles is increasing. So, and the motivation from this blooming of axion interest is manifold, one can say. First, perhaps one needs saying that the axion appears naturally in our favorite spheres beyond the standard model. And this it can appear as a Goldstone boson or as a regular quantum field theory string, Goldstone boson, but also in string theories, we have these so-called stringy axions that appear as imaginary parts of the moduli fields. And one can have something of the order of 100 of this in string theory. And in particular, the QCD axion is predicted, at least in string theory. Second, the existence of axions, it might be even favored by quantum gravity consistency argument, which tells you that, or at least this null de Sitter conjecture tells you that quantum gravity consistency here should not have the possibility of having de Sitter vacuum, and the fact that the axion renders the theta value unphysical in a sense, so that doesn't really matter what this 0 is in the QCD potential, actually prevents this type of vacuum. So, but this is still a bit controversial, of course. And another very interesting motivation for considering these particles is that from the fact that they arise from global symmetries, the low energy theory of whatever the high energy completion of these particles theories are, the low energy theory is very simple and contains only a few operators that one can use to direct the search for dark matter and axions in general to a very particular set of experiments. And this is also very motivating. Here in the most relevant part of the talk, I will be actually focusing on the photon coupling that has these different expressions, so 2 photons and 1 axion coupling. And the next most relevant coupling would be the coupling of the axion actually the electric dipole moment of the neutron. Finally, one can say that the strongest motivation is perhaps to consider axions is that some of the implications of these particles have already been observed. The first one is the existence of cold dark matter, as I was telling you before. And but there are some other hints of the existence of these particles. For instance, anomalous cooling of some stars have been observed, and the anomalous transparency of gamma rays. Although these hints are actually not experimentally very well established. So very well. The following graph summarizes our knowledge of axions as a function of the main parameter of the theory, which is the axion decay constant, a new energy scale that dictates the spontaneous breaking of the Peche-Kun symmetry and controls the size of the axion interactions and the mass, the axion mass. Small FA axions are not so weakly interacting, and they were soon very strongly excluded by laboratory experiments. And lowering FA actually decreases the interactions of axions, but still they could be produced in the interior of stars. And this would lead to anomalous cooling of stars that can be also constrained and excluded. So this removes a large chunk of parameter space. Actually, there are some systems that improve the matching between theory and expectations, where a bit of axion cooling would be welcomed. So these are here labeled as stellar hints and would point to the existence of axions in the 10 milli-electron-volt mass range. And finally, so recently we have been able to exclude axions at extremely low masses by the fact that we can measure black hole spins, because axions and axion-like particles with these masses, they have the right Compton wavelength to allow the exponential drain of the rotation of the black holes by creating that would create a super radiant cloud of axions around it, and then would slow down. So since we find axions with some spin, we can exclude the existence of axions in the right place to drain it. So this still leaves a huge parameter space where axions can be dark matter, and indeed, axion dark matter can be realized in all this mass range. So in this slide, we actually see the ranges of mass where axions can account for all the observed dark matter in the universe. You can see that the uncertainty is quite large due to the fact, I have to tell you that there are several possible mechanisms, and then depend on the axion model at hand and some aspects of early cosmology. So for instance, in the pre-inflationary scenario, inflation makes the initial condition of the axion field homogeneous in our universe. So all the universe starts with the same value of the axion field, which is here called theta 0. But since we don't know it, we could have dark matter with a value in the order 1. And then if we allow order 1 to be 0.1 to 3, then we would have this range between 10 to the minus 7, 10 to the minus 4. But even if you allow that the initial misalignment angle is 10 to the minus 3, we could have axion dark matter with a mass of 10 to the minus 11 without a great fine-tuning, one might say. Now, it's interesting that these calculations have been done by assuming that the universe is dominated by radiation during the QCD phase transition. And if one changes this assumption, for instance, allowing echination to dominate during that time, or matter decay, then these preferred regions of mass where axions would give you all the dark matter candidate, they shift either upwards or downwards, and they cover a huge mass range. Now, in the post-inflationary scenario, where inflation happens before anything that has to is related to the axion, so the inflation does not play a role, and the axion field is random inside of our universe, and its average density can, in principle, be predicted, and thus we could predict actually the axion mass, the axion dark matter mass. But this requires the numerical evolution of cosmic strings domain walls that appear in these models. And now different groups have done different analysis, and they are still not agreeing with each other, except in the fact that more or less, so in the broad range between 10 to the minus 5 and 10 to the minus, a few times 10 to the minus 4, here should be the dark, so the dark matter mass should lie here. And this is for values of n equals 1, or for values of n larger than 1, the ranges tend to be above the milli-electron volt. Here, n is the number of CP violating different CP conserving minima of the Axion field. And one has to say that finally, very recently, all the production mechanisms have been proposed lately. For instance, the stochastic scenario in which the Axion field would be produced by the quantum fluctuations of a second period of inflation, or the kinetic misalignment and parametric resonance of Ko et al. Recently produced that could produce Axions in the milli-electron volt range again. So as you can see, essentially all range of masses can be very easily covered. So, so how do we organize the search for Axion dark matter in this huge parameter space? Well, let us now then discuss the experimental search for Axion dark matter. So the fact that Axions are so light, as we're telling you before, we are talking about masses of milli-electron volt or less, means that the occupation numbers in the quantum sense are huge, and one can treat the Axion field, the Axion dark matter field, in a classical way. So we can consider ourselves at Earth inverse in this ocean of Axion dark matter waves. Now, from the expression of the dark matter density of the Axion field, we can obtain the value of the typical amplitude of the oscillations of the theta field to be of the order of 10 to the minus 19, which is extremely small. This is just by equating the energy density of the Axion field to the local dark matter density as observed by local measurements or estimates from the dependence with the radius in the galaxy. Well, this is a completely tiny amplitude compared with the sensitivity that we that we have from the measurements of the electric dipole moment of the neutron. So how are we supposed to measure this? Well, of course, the difference between the measurement of the electric dipole moment and what we are going to do is that now the Axion field is oscillating around the minimum. Okay, it's not static, but it's not equivalent to a static theta, but an oscillating theta. And moreover, these oscillations, they have a huge coherence time that is going to ease the experimental detection. And this is because Axions are trapped in the gravitational field of the galaxy, self-trapped, and the group velocity of Axions, which is the wave number of the Axion waves divided by the frequency, is of the order of the Beer velocity in the galaxy, which is 10 to the minus 3 only. So this means that if you look at the spectral density of Axions, you would have a peak that starts at the Axion mass, and the width of this peak is related to the kinetic energy of Axions, so the thing that goes above the mass. And since this is in the normalized limit proportional to b squared, then we have that the delta omega is of the order of 10 to the minus 6, 1 millionth time the size of the base frequency. And this means that the coherence time is going to be of the order of 1 million cycles, 1 million oscillations. So the Axion field will take 1 million oscillations to get out of phase. On the other hand, we will have a coherence length, because of the same uncertainty, a coherence length of the order of 1,000 times the Compton wavelength of the Axion. So the Axion field will be coherent, will have the same phase for 1,000 coherent Compton wavelengths. And this is going to help us very much. Not finally, the frequency at which the Axion oscillates is on the range of gigahertz for 4 microelectron volts. So if we consider the range from 10 to the minus 11 electron volt to 10 to the minus 3 electron volt that I showed you before, this means to deal with frequencies from kilohertz to terahertz, more or less. So relatively small frequencies. Yeah. So the amplitude of the Axion dark matter field is tiny, but we have a long coherence time. So let us use some resonance detection. Now, this slide shows the different experimental techniques that have been devised so far to search for Axions in different frequency ranges. As you can see, we are able to cover more or less the whole range, but with different experiments that each is sensitive to a few octaves. And actually, if you look at this lower part of the graph, you will see that when I list mature techniques, I only list one technique, the cavity, the so-called cavity experiment. The rest are in R&D phase, although many of them, they show very interesting progress, and we believe that we will soon have or our children most likely will have a full coverage of the Axion dark matter possibility. So I will be, in the following, I will be reviewing the most important of these experiments because I don't have time for everything. So the most important and mature experiment is so-called Resonant Cavity that was proposed by Piazzi-Kivi in '83. And this experiment uses high-quality microwave cavity immersed in a strong B field. Now, thanks to the axion photon coupling, the Axion dark matter is oscillating in this B field, is going to induce an electric field, and this, which is of very small size. This axion-induced field is equivalent to a power per unit area of 10 to the minus 26 watt per square meter. But if we tune the cavity to have a resonance at the Axion frequency, which is the central frequency at which the Axion is oscillating, then the cavity will build up coherently the signal, and then we will build up a signal which is proportional to the quality factor of the cavity that can be as large as 10 to the 6 and is typically 10 to the 5. So unfortunately, we don't know the Axion dark matter mass. This is perhaps the most important thing. So we need to scan over different resonant frequencies by tuning our cavity until the Axion is found. Therefore, the figure of merit is not the signal to noise in the experiment, but so-called scanning rate, which goes with the signal to noise squared. And so here you have that in order to scan an octave of dark matter mass in a year, the typical numbers that one require are magnetic fields of 10 Tesla. So because this is a dimensionless coupling of order 1 in the case for QCD axions, volumes which are of the same order as the Compton wavelength of the axion inside of the cavity, quality factor of 10 to the 5, and system temperatures when it comes to noise of the order of the quantum limit, which is the frequency, which is the axion mass, and the remaining parameters give you this typical value of the axion mass to the -7. So you see that this experiment is going to be able to scan an octave a year for mass of 4 microelectron volts and around, but it's going to be extremely difficult to go much higher in mass. Actually, this is what is shown in this graph that shows that how several experiments have been doing so far. The most important is the Axion dark matter experiment, ADMX, in the university, well, now in Seattle, that has actually the sensitivity in the coupling constant versus mass parameter space to reach the most celebrated or the benchmark Axion dark matter models, which are the KSVC and DFSC. Okay, so they have been able to reach this sensitivity. While the competitors, which are haystack experiment, the CAP, different CAP experiments in Korea, and Quark's experiment in Italy, are still on the way, working out the sensitivity to reach the QCD axion line to then start scanning if it's worth. So the Radius experiment at CERN, the Organ experiment at Australia, they're going to have, or they're mostly doing R&D to improve the sensitivity at high frequencies. And what you see here is that all of these experiments, they have more or less, they tend to limit or tend to have limited sensitivity by this line here, which corresponds to this scanning rate that I showed you before. So cavities of the typical geometric size, volumes of, cavities of the typical geometric size for a Compton wavelength given by the axial mass, magnetic fields of 10 Tesla, quantum limited sensitivity, and large quality factors would give you a bound on CA gamma versus mass, which is essentially has this slope 7/4, as you can see here. So there are very bright prospects therefore in the microelectron volt range, so that the ADMX experiments, Haystack and CAP, different experiments can actually find axions in these 10 to the -6 to 10 to the -5 electron volt range. But at lower masses, and at lower and higher masses, the situation is more complicated. So low masses, the issue is that the size of the cavity and the magnetic field has to be very large, and therefore the only thing that can be done is to use the B field as large as and the cavity as large as possible. And this has been proposed to do by the Clash collaboration that will use essentially cavities which are used in particle accelerators and B fields used in particle and high energy physics particle detectors and Frascati. And if we go at high frequencies, and well, it's much more difficult to go above this, as you can see in my comparison. At high frequencies, above 10 microelectron volts or so, one can still improve in my estimate and find the axion in this 10 microelectron volt and above range, but this requires taking every parameter to the extreme, like taking larger B fields using high superconductant, high temperature superconductor technology that can go a factor of 2 or 3 in magnetic field, going to the quantum limiting detection, going to millikelvin temperatures in system temperature, increasing the cavity quality factor to 10 to the 6 by using superconducting coating, using possibly new photon counters instead of linear amplifiers for detecting the signal, or even add the signal from many cavities coherently. So this is still possible, and we will have definitely some results in the 10, 20 microelectron volt. But going much higher to the 100 microelectron volt is going to be much more complicated. This because we will require, in principle, because the sensitivity goes down, the signal to noise is too small. What one would need, in principle, or building huge volume experiments like many cavities, but this will not work, I fear, to get sensitivity. So, or just to have ultra low and dark noise photon counters, but this might be an opportunity. Alternatively, there are different techniques than the microwave cavity technique. And the ones that have been proposed recently are dielectric telescopes, dish antennas, and plasma heloscopes. So let me just very briefly discuss them. Most relevant is perhaps this dielectric telescope that uses the large area dielectric disks that will radiate coherently to get a boost factor of the order of 10 to the 4 against this quality factor of 10 to the 5 that was getting you the resonant cavity, but in an area which is as large as the B field that you can build, which can be 1 square meter or so. So this can give you a huge boost. So the MATMAX experiment is actually working to make such an experiment at DSE since already 2017. And here the main challenges are to build a huge magnetic field and adjust the disks precisely. So I belong to this collaboration. So we claim that we can find the action in the 100 microelectron volt range, but we still have to build the magnet and do a lot of R&D. And so the experiment will not start until 2025 at the very earliest. So other interesting ideas are the plasma heloscopes and dish antennas. So the first explode the fact that the axion-induced electric field is actually inversely proportional to the dielectric constant of the medium in which it is excited. So if we are able to build a medium that has the dielectric constant that is much, much more than 1, this will boost the signal enormously. So Lawson et al. And the group of Wilczek in Stockholm University are all working to produce such an experiment, and they have chosen to go in the direction of using thin wire nanomaterials. So, and with the estimates that I'm doing, they think they can reach a similar parameter space than MATMAX. Finally, dish antennas, these experiments, they aim at maximizing the area in spite of losing the quality factor enhancement completely. 2 such experiments are currently being considered, and they, in principle, they don't have the sensitivity to find standard QCD axion models unless one uses a miraculously small dark count noise bolometers that still, I think they don't exist, but they might in the future. So yeah, we'll see. But nevertheless, they're very interesting. So, so this covers pretty much the range between 10 to the minus 7 microelectron volt up to millielectron volt or so. But if we want to go much below, we have to switch gears and change technique. The most perhaps interesting technique is the so-called dark matter radio. This idea is based on a similar phenomenon that the cavity. So here, the axion dark matter in this will excite in this toroidal field an axion-induced electric field, which is also toroidal, which oscillates in time, and therefore generates a dipole magnetic field along the toroidal axis, this here. And this can be picked up by a coil and detect, okay? So the induced field is not actually resonant, but the resonance will happen in a LC circuit coupled to the coil, okay, here. And this allows to have resonances which are much smaller than 1 over R, the size of the toroid. So you can go to low masses even if your detector has a particular size. Now there are 3 collaborations in the US building such experiments: the Abracadabra, so the dark matter radio, Abracadabra, and SLIC. And so you see here the Abracadabra concept is just this superconducting cylinder. Sorry, this toroidal magnetic coil, and instead of using a pickup coil, they use a superconducting pickup cylinder. They have already built this 10 centimeter prototype that has very moderate sensitivity here in this coupling to photons versus mass range. But going to 1 meter or 4 meters, the sensitivity will decrease such that they will be able to explore axions in this 10 to the minus, even 10 to the minus 9 range, all the way up to 10 to the minus 7 or so, even higher. So they could find axions in this gap immediately below. Finally, at even smaller masses, we have the most direct probe of axion dark matter. We can actually here aim at measuring the oscillating electric dipole moment of the neutron. This concept was put up by Sajid Rajendra and Peter Graham and Dima Budker a few years ago, and it consists on having an oscillating, or the fact that the oscillating electric dipole moment in an external E field leads to a spin precession that builds the parallel magnetization of a sample, just like oscillating B fields will grow up the parallel magnetization in a transverse B field. And therefore, they can be sought after with a squid pickup loop here, like in regular NMR. So this is like regular NMR, but instead of with an oscillating B field, with an oscillating electric field. So the resonant increase of the magnetization happens when the spin precession matches the oscillation of the EDM, so which is given by the axion dark matter mass. So you can just change the oscillation frequency by changing the strength of the external magnetic field. And this has some limitations, but this allows you to scan a very broad parameter space. So the signal is tiny. So in order to maximize the signal, we essentially have to build a properly sized sample with large electric fields in the position of the nuclei and minimize spin decoherence, etc. So the first experiment has been done by the Casper collaboration by this gentleman and colleagues, which are based in Mainz and Berkeley. And they have already exploited a 5 millimeter sample of lead titanate during a few days. So they have searched this experiment and they have been able to exclude this parameter space, which is something like 15 orders of magnitude away from the QCD axion line. However, the sensitivity in all these range, you see, it goes much better. And they think that going to 80 centimeters samples, it would allow them to go down here to this blue line that actually touches the axion prediction. So they would be able to find axions at least below the nanoelectron volt mass down to 10 to the minus 12 or so. So this is extremely exciting, but it will take a few years still. So with this, and noticing that I've already overspoken quite a bit, for which I'm truly sorry. I would like to reach my conclusions. So I think the Axion would solve the strong CP problem and would be an excellent cold dark matter candidate. The second is a result of the solution to the strong CP problem. So it's quite a minimal assumption. It is very nicely motivated by a physics beyond the standard model, by simplicity and a few hints like the existence of dark matter and perhaps some other astrophysical hints. It is very interesting that one can predict in principle the Axion dark matter model by giving the cosmology and a few parameters of the Axion model. And this can help us to guide the search for Axions and also learn about cosmology and Axion models in case of a detection. And experiments are underway in all the Axion dark matter range, from the ADMX human size to MadMax, which is a slightly bigger but looks at high frequencies, or Casper and the dark matter radio. So I just wanted to also say, oh, I deleted something here. Yeah, my apologies. So as a final message, please apologize. I know that there are many more dark matter experiments I have not talked about. I've tried to put them in this plot. So that you know that there are many more initiatives to search for Axions, particularly high frequencies, that I have not touched upon. You can always ask me about them, either here or privately. Thank you very much.
Thank you, Javier, for a very nice talk. Despite the fact that you went over, we had only one question in the Q&A, and perhaps there will be other questions in the discussion boards. But I was wondering, I think this is actually kind of an interesting question, or at least it should be straightforward, hopefully answer. Normally, as particle physicists, we might think of coupling constants as being dimensionless. Why is it that the coupling constant that you have here in your Axion models have units that are like 1/GeV?
Yeah, so this pertains to the fact that actually the Axion is a Goldstone boson, and all the interactions of the Goldstone boson are to be suppressed by the energy scale of the spontaneous symmetry breaking, which in this case is Fa. So very often, let me just go back to my definitions of couplings. So very often, so as you see here, this operator is dimension 5, and therefore the coupling constant has to be 1/energy. And this energy is nothing but the Axion decay constant. So when we write coupling constants of Axions as G, these G's typically include 1/Fa inside. But it's a bit tricky because when we do this with the Axion coupling to electrons, as you can see here, the operator, so the dimension of this operator is 4, and this therefore is dimensionless, but it also includes 1/Fa. The thing is that we have also included a factor of the Axion mass in the definition. But all these couplings, they have 1/Fa in the definition. And this comes from the fact that the Axion field appears as an angle in the Lagrangian. And this angle is equal to the Axion field with dimension 1 divided by the energy scale, which is Fa. So every time that theta appears, there will be a 1/Fa accompanying.
Thank you so much, Javier. I think now we should move on to our next talk since we are a little bit behind schedule. Hi, Yanni.
Hi.
Hi, Yanni. So Yanni is going to talk to us about light dark matter, again, covering both the experiment and the theory. Take it away.
Okay, thanks so much. And hi, everyone. It's really nice to meet you all, even if only in this virtual setting. I hope we swiftly return to days where we can be meeting in person and chatting over coffee. So I'm a faculty member at Hebrew University. I'm sitting here in Jerusalem in Israel, and I'm going to be telling you guys about a topic that I've been very excited about over the last few years, and that's light dark matter. As in Jody said, I'm going to be talking both from the theory perspective and the experimental perspective. So my outline, as I said, is very simple. I'm going to hope to convince you why light dark matter I think is interesting, and then we're going to talk about how we can hope to explore it, and we're going to go about this both from the theory side and the experimental side. So let's start at the beginning. As I'm sure you know, our universe is dark. Nearly 30% of the energy content of our universe is in the form of dark matter, and I think it's no secret that the star of the show in this context for the last 40 years or so has been the WIMP, the glorious WIMP, with, of course, appropriately stated caveats about axions, which we just heard a lot about from Javier. And the idea is extremely simple for the WIMP. If we have some particle in the early universe which interacts through 2-to-2 annihilations, we can have a relic abundance that's left over. And if we just parameterize that annihilation cross-section as some coupling squared over mass squared, then we find that there's a particular size for the cross-section that gives us the right relic abundance, or said another way, there's a relationship between the mass and the coupling that says that the mass should go like the coupling times around 30 TeV. And so it happens to be the case that if this coupling is of order, the electroweak coupling of order 10 to the -2, then the electroweak scale emerges. And this is the WIMP miracle. And this WIMP miracle has, of course, been our dominant notion for dark matter for over 4 decades. And it's really easy to understand why, because it's extremely simple and it's extremely predictive. And as this has been our dominant notion for dark matter for so many years, it's also been guiding our experimental searches. And we search for dark matter, of course, in a variety of different ways. We search via direct production, where we smash standard model particles on each other, hoping to produce dark matter particles. And this is, of course, for instance, what we do with the LHC. We also search via direct detection, where here we take some big pool of standard model particles that we know and understand, and we put it in the lab, typically deep underground, and we hope the dark matter will come and scatter off of it and leave some imprints in our detector. And we also search via indirect detection, where we look through fancy telescopes and satellites to the sky and hope to see dark matter annihilation or decay products into standard model particles, which we can observe. And we've been searching for some time, and we haven't yet found these particles, right? These experiments are getting increasingly sensitive, and this is true on all of these frontiers, and doing a phenomenal job at probing the WIMP, and yet we haven't yet detected dark matter. And so the status of dark matter in 2021 is that our dominant notion is really being challenged. And I think this is a great opportunity for new ideas to emerge. Because if you think about it, that WIMP mass range that we've been so focused on for so many years really spans just a small fraction out of a vast parameter space in which dark matter can reside. Okay, dark matter could be many, 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 many orders of magnitude above or below the WIMP mass range. And so what I'm going to focus on in this talk is on the possibility of going lighter, in particular between 3 to 6 to even 12 orders of magnitude lighter than the WIMP. This is a field that's seen a lot of activity in recent years, both from the theory side and the experimental side, and I'll hope to give you a taste of both of these. And as you can imagine, as we move forward in one, of course, this new information and these new ideas sort of feed into the other as we press forward. So let's start with the theory perspective. So new theory ideas that predict light-dark matter are extremely abundant. I've put together sort of a list over here. This is by no means a comprehensive list, okay? And what I'd like to do is walk you through just a few of these examples to give you a sense of how easy and how generic it is to have light-dark matter. So here's my first example. It's exactly the WIMP, okay? So let's still look at a 2-to-2 annihilation process, exact same annihilation cross-section, exact same relationship between mass and coupling to give us the right relic abundance, except now instead of taking a coupling that's of order the electroweak coupling, let's just take a coupling that's much smaller. We naturally get dark matter that is substantially lighter than the weak scale. The second example are forbidden channels. And for this, we can still look at the same 2-to-2 annihilation process of dark matter, except now we can think of the kinematic regime where the sum of the incoming masses is smaller than the sum of the outgoing masses. So if we were looking at a zero temperature situation, this process is of course forbidden. But the early universe is thankfully a thermal environment. And what this means is that in the early universe, this process can occur through living off of the Boltzmann tail of the dark matter particle distributions. And so if we write down the relationship between mass and coupling that we need in order to obtain the right relic abundance in this case, we find something that starts off looking very similar to the WIMP, but now we have this additional exponential suppression factor, which is exactly coming from this Boltzmann suppression of the number densities of the dark matter. And so in this case, we naturally get dark matter that is exponentially lighter than the weak scale. My third example, what if what's most important is not so much how dark matter speaks with other particles, but more how dark matter speaks with itself, okay? So in this case, the first process that could change the number of dark matter particles in the early universe would be 3-to-2 self-annihilations, where 3 dark matter particles come in and 2 dark matter particles shoot out. And if we parameterize this kind of weird object, this 5-point interaction, or this 3-to-2 cross-section as some coupling cubed over dark matter mass to the 5th, and in terms of dimensions, this is the right dimensions for this odd quantity, and you solve what the relationship between mass and coupling has to be in order to get the right relic abundance, you find a very, very different relationship than the WIMP. Here we find that the mass of the dark matter should go like this self-coupling times around 100 MeV. And so here it happens to be the case that if this coupling is an order 1 coupling, a strong coupling, then the strong scale emerges. So instead of a weakly interacting massive particle, we now have a strongly interacting massive particle, or instead of a WIMP, we've named this a SIMP. Now, if all we had, this gives us dark matter that's typically between the MeV to GeV mass range. Now, if all we had was just this 3-to-2 process, then that 3-to-2 process is pumping heat into the system because the 3 dark matter particles that come in are shooting out 2 dark matter particles that are each more energetic. And so there has to be some way to shed this heat. There has to be a way to dump entropy out of the dark matter sector. And the way that we can do this is, for instance, by thermalizing with light standard model species that are abundant at the time of freeze out. And so we want this thermalization process to be active at the time the 3-to-2 freeze out is happening. And so in the SIMP mechanism, we have these sort of 2 knobs that have to exist. Now you can ask yourself, in the case of SIMPs, as we just said, we have these 2 knobs, and the 3-to-2 process decouples first, and later decouples this thermalization process. What would happen if the order was reversed? And in this case, you find something very curious. You find that the relic density of dark matter is now exponentially sensitive to the elastic scattering cross-section. And so in this case, what we find is that the elastic scattering cross-section is determining the relic abundance. And so this has been named the elastically decoupling relic, or in short, an elder. And in fact, if you look at the relative size between these 2 couplings, the dark matter standard model coupling versus these 3-to-2 self-annihilations of dark matter, you find that just depending on the relative size between them, you actually flow in the theory in sort of the parameter space between a regime in which you're a WIMP-like dark matter candidate to a regime in which you're a SIMP to a regime in which you're an elder. And so these 3 a priori very different mechanisms are all just different regions of populating dark matter parameter space. So I've given you a few examples of how one can obtain very easily light dark matter from the theory perspective. And now I want to talk a little bit about experiments. So we, of course, have many experiments, and I mean here, by experiments, I mean direct detection experiments that search for dark matter in the lab. And although we have many experiments, they all roughly follow the same blueprint. So the idea is that we have some target that's sitting in the lab, typically deep underground. And the hope is that dark matter is going to come in, it's going to hit that target, the system is going to react in some way, and we hope to measure that reaction, right? So dark matter comes in, hits my target. The target is now going to shoot out electrons or phonons or photons or something. Some excitation is going to happen, and we want to measure what it is that occurred. And here's a typical plot that I'm sure you've seen many times, that direct detection experiments show us, which shows us, since we so far haven't discovered dark matter or detected it, it shows us the size of the constraint as a function of the dark matter mass, the size of the constraint on the dark matter nuclei interaction cross-section. And you see common to all of these different colored curves, which represent the different amazing experimental results, they sort of all shoot up in this region when the dark matter mass drops beneath a few GeV. So what's going on in this area? Why are we losing sensitivity when the dark matter mass is beneath the GeV scale? And the reason is that what these experiments are typically doing is looking for nuclear recoil signals, okay? Now the energy that's deposited for nuclear recoil goes like the momentum transfer squared in the process over twice the target mass. Momentum transfer, roughly the dark matter mass times its velocity in natural units of order 10 to the minus 3. Okay, and of course, if we want to detect these nuclear recoils, then this energy better be above our thresholds, which are typically of order the keV scale. But you can really understand everything that's happening just in terms of thinking of billiard balls. Okay, so if I'm a dark matter particle that's a WIMP, which these experiments were designed to do, everything makes perfect sense. I have my big ball, my big WIMP that is coming in, and it's trying to kick a big heavy nuclei, a big ball that's sitting in the lab. And of course, it's going to be able to do that, and we're going to be able to measure this reaction. But what happens when dark matter is much lighter? In this case, the kinematics is more like a tiny ping pong ball that's trying to give a big kick to a big bowling ball. And then it's just not going to work. This light dark matter can't give a big enough punch to kick that heavy nuclei. And this is why we lose sensitivity when the dark matter mass drops beneath the GeV scale. And so if we want to be sensitive to light dark matter, it's actually smarter to scatter off of something lighter, such as electrons, where the kinematics is more well matched, and that light dark matter can give a big punch, can give a big kick to the light electrons. And this basic understanding really sits at the core of many of the new proposals that have been put forward in recent times. And so to understand those, let me provide you with sort of the following energy guideline. Okay, so if we want to be talking about detecting dark matter scattering events, then in such a scattering event, the maximum energy deposit that you could possibly have is the entire kinetic energy that the particle is carrying. Okay, so that means kinetic energy, mass times velocity squared again of order 10 to the minus 6. Okay, and so this means that the maximum energy deposit is 6 orders of magnitude beneath the mass if we're talking about scattering. And so if we want to be sensitive to GeV scale masses, then we need systems that are sensitive to KeV energy deposits. But if we want to go 3 orders of magnitude down and go to detect dark matter at the MeV scale, then we need systems that are sensitive to much smaller energy deposits of order the EV energies. And if we want to be really greedy and go all the way down to the warm dark matter limit at the KeV scale, then we need systems that are sensitive to really tiny energy deposits of milli-electron volt. And so we can organize all of the new proposals that have been put forward in the literature, really sort of organized by the size of the energy deposit that they're sensitive to. And so I've just put some of them down over here, and you see there are many of them. A lot of them use these interactions with electrons. Some of them also use, in a smart way, interactions with nuclei by looking at phonons. But there's really just been this explosion of interest and new ideas in recent times. And so what I'd like to do is, again, just sort of walk you through a few of these to give you a little bit of a sense of the types of materials people are thinking about, the type of detectors, the types of processes, the type of detection philosophies, to sort of open your mind in this direction. So I'll start with my first example, which are really the first ideas that were put forward almost a decade ago. And so maybe dark matter would come in and ionize an atom. Or maybe dark matter would come in and deposit enough energy to to promote an electron from the valence band to a conduction band in a semiconductor. And so if you think of ionization energies, for instance, for xenon, this is of order 10 eV. In typical semiconductors like germanium or silicon, and we've recently been able to show that also diamond and silicon carbide are excellent for this purpose. The gap over there is typically of order an EV or a few EVs. And so based on that energy guideline, this tells us that these systems can in principle be sensitive to the MeV mass scale of dark matter. And even though these ideas were originally put forward by theorists, they are being experimentally realized. And so from the atomic ionization direction, xenon 10, 100, 1 ton has certainly been leading the way when we have constraints from that. And from the semiconductor front, both Super CDMS and Sensei, as we also heard earlier today in Mark's talk, these really using silicon devices have really been putting impressive new limits that are sort of going in this sub-GeV mass range. But what if we want to go to even smaller masses? Okay, this is something that we fundamentally can't do with electronic excitations in these systems because of the energy gap. So in this case, enter my example number 2, which are superconductors. So in superconductors, the ground state is no longer free electrons, but it's energetically favorable for them to sort of follow the buddy system. And so they pair up in pairs that are called Cooper pairs. And the binding energy of these Cooper pairs, which is the gap of the system, is of order milli-electron volts. And so again, based on that energy guideline, this tells us that these systems could in principle be sensitive to the KeV mass scale of dark matter. So the idea would be that dark matter comes in, scatters with these Cooper pairs in the superconductor, deposits enough energy to break those Cooper pairs apart, that's going to create some excitations that we hope to detect. And when we first put out this idea a few years back, we had used a philosophy that's very similar to what Super CDMS is doing with semiconductors, which is an excitation concentration philosophy. But what I'd like to go through right now is a more recent idea that we put out in our PRL in 2019, which is a sensor plus target philosophy. So for this, our technology of choice is superconducting nanowire single photon detectors. It's a very long name, and in short, it's acronymed of SNSPDs. And these are very sensitive devices that are broadly used in quantum information science. Okay, they've been developed for quantum sensing purposes. But the idea is that dark matter would come in. So we have these nanowires, and they're sitting sort of in a circuit that's biased close to a critical current value. The idea is that dark matter would come in. It's going to ram an electron in this nanowire. That creates some hotspot, which makes the electron sort of diffuse away. That's going to create a resistive region across this nanowire, which results in a voltage pulse that we can read out. And essentially, what we've proposed is to use this extremely mature technology for the first time to apply it towards the dark matter detection. And so the idea is that we use simultaneously this nanowire as the target with which the dark matter is going to interact, as well as the sensitive sensor that senses that such an interaction had occurred. And of course, to hopefully build up in mass, one would multiplex many of these things. And we already actually have an existing prototype device that's been giving us science results already, which already serves as sort of a proof of concept. And I'll be showing you some of those results a little later today. Now, what about directional information? So certainly, in sort of if we think about the original sort of excitation concentration idea with what supersedium mass is doing and our proposal for bulk superconductors, if what's happening is that we sort of let excitations inside our bulk material just sort of ricochet around until we collect and detect them, we lose this directional information of where dark matter was coming from when we're seeing these secondary particles. Now, detection has long been recognized as a powerful role in dark matter because it gives us a way to separate our signal from background that gives a daily modulation rate. And so it would be really amazing if we could retain that directional information. And this is something that we can hope to do if what we're observing, for instance, is the primary electron with which we interacted. So this is something that we could hope to do in general for two-dimensional targets. And I'm going to tell you the story in the context of graphene, but just keep in mind that you could do something very similar for these nanowires as well. So this is my example number 3, graphene. So graphene is a two-dimensional material with a vanishing or nearly vanishing band gap, but we don't have to know we're not going to use any of the beautiful properties of graphene. All we need is the fact that in order to eject an electron from the material, we have to overcome the work function, which is of order a few eV. And so based on that energy guideline, this tells us we could be sensitive to MeV dark matter masses. So the idea would be that dark matter comes in, it's going to scatter with the valence electrons, deposit enough energy to eject the electron from the material, and we're going to detect that ejected electron. Okay, so this is an eject and detect philosophy. And the real strength of this proposal comes from the fact that if you track the direction of that ejected electron, it turns out that it's following the direction of the incoming dark matter. And so this setup naturally gives us forward-backward discrimination power, which can separate signal from background. Because imagine, at some point during the day, if this is my graphene sheet, the dark matter wind is coming in exactly from underneath. And so I have an electron that's ejected in the forward direction, which we detect. But now fast forward 12 hours later, as Earth is rotated around its axis, now the relative orientation is exactly reversed. So if this is my graphene sheet, the dark matter wind is coming in from on top. The electron is now ejected into the substrate, where it's either not detected or detected as something different. Okay. Now, you might think that, so in order to build up a large amount of graphene, let's say we wanted 0.5 kilogram of graphene, that means we need billions of centimeter squared crystals. And I've done the computation. We basically have to tile the entire old area of the old city of Jerusalem. And under the assumption that nobody's going to let us do that, the way that we could hope to build up in this type of mass, we're imagining that we use a compact geometry where we get this large mass by using many, many stacks. And for the size that we're imagining, this is something that could roughly fit into a 10-meter cubed type of volume. And you might think that it sounds a little crazy to ever think of acquiring such a large amount of graphene until you find out that there's an experiment that plans to do just that. There's an experiment that's called Ptolemy, originally proposed to detect relic neutrinos through their capture on tritium. And they intend to have their tritium sitting on 0.5 kilogram of graphene. And so what we proposed is to sort of borrow their bare graphene sheets and run this experiment before they load it with tritium as a directional detection dark matter experiment. And this idea has been officially adopted by the Ptolemy collaboration, which, as you see, is now also officially an experiment for directional detection of dark matter at the MeV scale. And it's certainly a lot of fun for me as a theorist to be seeing sort of the interworks of a big experimental collaboration from the inside. Okay, so I've given you hopefully a few examples of different types of materials and detection philosophies for light dark matter. But anytime you have some new material or some new idea, you have to go ahead and compute what is my event rate? How many events am I going to see? And the rate, of course, has a whole bunch of factors that come in. We care about the target density. We care about the dark matter flux that's coming in. Properties of the target itself, or often some condensed matter physics comes in, and of course the size of the interaction cross-section, which is where the particle physics really sits. And so here's an example of, here's a plot that we put together in a community report a few years back, which shows you sort of the expected scattering reach of many different proposals. So on the x-axis, you see here the dark matter mass. Notice this is in MeV units now. And on the y-axis is showing you the size of the dark matter electron scattering cross-section. In this case, this is for a light meteor with some reference momentum transfer, as is typical in the field. So if you look at all of these colored curves over here, which are sort of losing sensitivity at the MeV scale, these are all of the different ideas that have an energy threshold roughly of the EV scale. And so amongst those, let me just point out this dashed green one, which is showing you the reach of this idea using graphene. And you see that compared to other ideas with similar energy gaps, it does better than some, worse than others, roughly performing the same. Importantly, out of all the ones that are exhibited over here, it's the only one that has this directional detection capability, which if we were to observe dark matter signal would be so important to actually understanding, is this signal or is this background? And down here in this sort of dotted green curve, you see the reach of superconductors, which is really just amazing. And to show you that this isn't science fiction, as I mentioned, we already have an existing prototype device for a nanowire. So this is a tungsten silicide nanowire. It's super duper tiny. It's around 4.3 nanograms. We know that it is sensitive to 0.8 EV energy, possibly even lower, but we know for sure 0.8 EV threshold. And at the time that we had published our original paper, we had observed it for 3 hours on a surface run and observed no dark counts. By now, we actually have 180 hours of data. And so hopefully coming soon to an archive near you, you'll be able to see our official results. Here are preliminary new bounds that we can place on dark matter scattering. And so this the solid curve is showing you previous bounds, whereas the dashed curve is showing you our new bounds. And the shaded gray are the existing constraints on this parameter space. And what you see here in these additional colored curves are showing you as we push to larger arrays, pushing the threshold even lower while keeping dark counts low, we can really hope to probe really amazing new regions of dark matter parameter space. And indeed, we're nowhere near the fundamental limits on the thresholds of these devices. My experimental quantum sensing collaborators that I've been working with on this topic recently put out a paper that shows they've demonstrated, again, with tungsten silicide nanowires, sensitivity to 10 microns. So in particle physics language, that would be 125 milli-EV energy thresholds. Okay, so we are definitely nowhere near pushing the fundamental limits on these thresholds. And just to sort of bring us back to this plot, you see over here, this dotted blue curve is showing you, if the nanowire that we were performing the measurements with turned out to be sensitive to such a threshold, then you see how we could even go further in probing new light dark matter parameter space. And most recently, we've been able to sort of develop a new formalism for phrasing how we can compute dark matter electron scattering rates. And that's because these rates in any material are completely determined by the dielectric function or the loss function of the material, which importantly is something that we can go ahead and measure. Okay, and this is true for any interaction of dark matter that's coupling to electron density. So any spin-independent interaction, whether it's a scalar or a vector mediator, it abides by this. And the strength of this is really that historically the way people have computed rates is by looking at, by sort of thinking of the single particle excitation picture. But that really misses collective modes that are just automatically encompassed and included. All of the many body effects of the material are included already in this new formalism. And what this gives us is the opportunity to really identify promising new materials for dark matter detection. And just to give you an example, you see over here, again, this is showing you a projected reach for cross-section versus dark matter mass. And if you look here, this green curve is a new type of material which we've proposed, heavy fermion systems, which just thanks to sort of where the collective modes sit in these materials, can be well matched to the energy scales that we're interested in. And so we can really hope to sort of determine optimal materials for dark matter using this new formalism. Okay, so hopefully I've convinced you that light-dark matter is definitely a very active field of research. This is true both from the theory perspective as well as from the experimental perspective. And importantly, I think the ideas are by no means exhaustive. I think we're just really at the beginning of sort of putting forward a proper and full and comprehensive program for light-dark matter detection. And if there's one thing that I've learned over the last 5 years dealing with this, is that it's totally fine for an idea to seem crazy at first, because it might just be that your crazy theory idea turns out to be completely generic in theory land, or that your totally crazy idea, there's an experimentalist in some other field who happens to have a device sitting in their lab which can already place the strongest limits on dark matter in a certain mass range. And I really think that the best ideas might be ahead. And I'll also say that for me as a young scientist in the field, I find it extremely inspiring that, if I think of where the dark matter program was 10 years ago, we had all these incredible, we still have these incredible experiments that are searching for WIMPs, and those are going to continue to operate in full force in upcoming years. But if dark matter was lighter than the GeV scale, we didn't have good ideas. And just looking at the incredible amount of activity that's been happening and the wealth and richness of the new ideas that have been put forward in recent years, I just think it's really, really amazing. And importantly, these ideas are really being worked on together between theorists and experimentalists. And this interdisciplinary work doesn't just stay within the realm of particle physics, but it's really an interface between particle physics and condensed matter physics, quantum information science, precision measurements, AMO, etc. And so I'll just end by saying that if you have any crazy new ideas for dark matter, you're very welcome to be in touch. And I'll thank you for your time.
Thank you, Yonit. So we actually are getting quite a number of questions, or a few questions coming in. And I know that we've already gone over, so I'm going to ask one of the questions, and then perhaps the other one can move to the discussion. But so there's a question about the results that you had in your SN-SPD detector. In particular, did you see any cosmic rays, or what do you expect the cosmic ray interactions to be? And what are the dominant backgrounds of that measurement?
Great. So I can say, I'll give full details about our original paper from 2 years ago. At the time, we had seen 0 dark counts in this device. So this was just you take your nanowire, and once you know that it's working, and you send light on it, and you know what your threshold is, then you take out the light and you just sit there and see what happens. Is it clicking or not clicking? We watched it for 3 hours for around 10,000 seconds, and no clicks. Okay, so that was a 0. That was a 0 event. Don't see anything, and so you can set limits based on that. In the 180 hours of data, we see 4 events, 4 dark counts. And so in making sort of the projections or our new constraints, we take those into account. And certainly the next step, and this is really important to emphasize, the SN-SPD was a completely non-dedicated experiment. This wasn't a device that was designed to be a good dark matter detector or anything. This is just a sensor that was designed for something else, related to dark matter, but not to be a target plus sensor itself. And it just happens to be that nanowires are a technology that is extremely quiet. It's known to have very low dark count rates. There's sort of state of the art has very low dark count rates, and the people who are the quantum sensing experts who are involved in this work are really the best, or amongst the best in the field. And we can certainly hope to do, I believe, much better with a combination of designing the nanowire so that it'll be sensitive to even lower thresholds, and performing not just a surface run, without having a lot of shielding, but really trying to put it in a super quiet environment, bringing it down, trying to sort of reduce any sources of that sort. But for the measurement that we have, these are really, we don't know what we're seeing. They see 4, and we include that in our results.
Okay, so I think the other questions, so all the questions that we got actually are around backgrounds and what the backgrounds are in general in these types of experiments. So that sounds to me like something that if we were in person, we might do over coffee discuss what possibilities are. I think they're rather newish experiments, and so perhaps some of it is that we're still discovering it. But perhaps this is a discussion that we can take offline into the discussion board then
Sure.
to continue that. But just to give you a reflection of what I'm seeing the questions to be, it does seem that people are mostly concerned about backgrounds.
Okay, great.
Excellent. Well, thanks again, everyone, for coming to this session. I think we're on break now until the next start of the next session, which looks to start at 5:17 or 5:10, sorry, 5:10, and seems to be a series of panel discussions. So thanks everyone for joining. Thanks to Yonit and Javier for wonderful talks and great discussions this morning. And we'll see everybody else in the next set of sessions. Thank you.